Welcome to the second lecture by Professor Kauffman. He is going to talk on mock Alexander polynomials. Professor Kauffman, you can start.
Well, no, now I have to bring it up again. Sorry. Okay, there we are. All right, so it's a great pleasure to be able to give a talk and celebrate the birthdays of Andrei and Valeriy. I'm very happy to be able to talk in this seminar. Everyone can hear me, yes?
Yeah.
Good. This talk is about what I call mock Alexander polynomials and marker state sums, and it's joint work with Neslihan Gugumsu. We're going to be looking at various invariants that can be produced by state sums of the kind that are indicated on this slide, where a state is a choice by each region that is not designated by a star of one of the corners in that region, one of the vertices. It's a state. And each vertex in the knot diagram, which will occur in various contexts, will have vertex weights that are indicated as I've indicated them on this slide. And then the marker, which occurs in one of the four positions, will match with one of the vertex weights. And then one takes, for a given state, the product of the vertex weights and sums over all the states. But where does this come from, and what kind of generalization am I going to talk about? Let's begin at the beginning. So Alexander in 1928 wrote down a combinatorial algorithm for his polynomial, the Alexander polynomial. The combinatorial algorithm is related to the Dane presentation of the fundamental group of the complement of the knot, but I won't go into how it's related to the Dane presentation. I'll just show you Alexander's algorithm. Alexander writes down a module relation for each crossing in the diagram, where the module is generated by the regions in the diagram. And the module relation is obtained by a particular way of marking the crossing. You put two dots to the left of the undercrossing line, and then you write down a relation. And I write it down a little bit differently from Alexander, who had signs in it, because for my purposes, the signs don't matter. So we will get the Alexander polynomial without having to worry about these signs of Alexander. So you write down ax plus bx plus c plus d, and it's a module relation. And then Alexander took a determinant that is related to this module. And that gave rise, of course, to the more modern definitions of the Alexander polynomial a little later on. And in fact, this module is the Alexander module. So here I'm showing it to you in the Alexander form. Alexander would write module relations, one for each crossing, and then you could put them into a matrix in the usual way, where the columns of the matrix correspond to the generators of the module, and you place the coefficient of the module generator underneath it in that column. So XA plus B plus XC plus D relation is the same as what came from vertex, the left vertex there. And you get 3. And you find yourself with a matrix which has 2 more columns than it has rows. And Alexander's definition is to eliminate 2 columns that correspond to adjacent regions and take the determinant of the remaining one. And that is the Alexander polynomial, well defined up to equals dot, which I've illustrated in the upper part of the slide. Equals dot means up to plus or minus x to the n. So it's a determinant obtained as a certain relation matrix. And if you, later on, people pointed out that this polynomial generates the ideal of polynomials that annihilate the module. And there are many other reformulations of the Alexander polynomial that came historically after this. I'm looking at Alexander's original definition here. And you'll notice that when you take the determinant here, you get x squared minus x plus 1, which is the well-known Alexander polynomial for the trefoil knot. Now, what we're going to look at is the combinatorics of this determinant at first. If you take the determinant and look at the products that it constitutes when you write it out as a sum of products, then an individual product corresponds to a placing of rooks on the checkerboard of the determinant matrix in such a way that they do not attack one another. In other words, you choose a certain permutation, and that permutation corresponds to having uniquely chosen one vertex for each region that is not designated as out of the game. So the regions A and B are out of the game, and otherwise, region C, for example, chooses 1. And there you see region C chose 1, and region D chose 3, and region E chose 2. And the choices are then indicated by these markers. And so I call this a marker state. And that marker state is exactly one of the terms in the determinant expansion. And notice that a dot corresponds to an x in Alexander's method, and no dot corresponds to a 1. So if the marker meets a dot, then you will evaluate an x. So in this case, you'll get an x, no x, and no x, and you'll get a single x, and that's the x times 1 times 1. So the terms in the determinant correspond to the states, and therefore we can say that the Alexander polynomial is obtained by summing over the states of the diagram and multiplying the contributions of each state, the vertex weights in the Alexander case. And then we have to multiply by signs because each permutation has a sign. And then something fortuitous happened, which wasn't obvious immediately. And that is that if you take -1 to the number of black holes in the combinatorics, and I call a black hole a marker where two oriented edges are going inward around the marker. So this is a black hole, and that's a black hole. All right. So you count the parity of the number of black holes in the state, and that turns out to calculate a sign just as good in harmony with the sign that would come from the determinant. So one ends up with a formula for the Alexander polynomial, which is entirely described in terms of the combinatorics of the diagram and doesn't need the matrix anymore at all. One of the things that I did with this a long time ago was to give a model of the Conway-Alexander polynomial. This was a long time ago. And what you can do is you can change the vertex weight set. There's a story about how to change it, of course, but I won't go into that. But you change it to what I showed you on the first slide or what's happening here. These variables are inverses of one another, W and B, or S and 1 over S. There's a sign there, a minus sign, and that minus sign is in there because we are doing this model where where the number of black holes is counting the sign. So if I simply put a sign in the black hole position, then I will get -1 to the number of black holes of any given state. So that means that we now have, you can check, of course, there's some exercise to do here, that we now have something that can be checked to be invariant under all Reiter-Meister moves, independent of any matrices that were originally in the definition, by taking the state sum and summing over all the marker states, and independent of the placement of the adjacent stars in the state. And it will satisfy the Conway identity. It's a nice bit of combinatorics why it does that. And that was all done a long time ago, but we got to looking at this again. We got to looking at this state model again because at first we wanted to extend it to natoids. And a natoid, as you probably know, and we'll get to some pictures of one in a moment, a natoid is a knot diagram, which is a 1-1 tangle, except that the endpoints of the tangle can be in different regions. And you do classical knot theory with natoids by moving it around, but not allowing it to cross over its endpoints. The idea of studying natoids for their own sake is due to Turayev. Now, the states have an interesting structure, and it's worth mentioning them, and then I'll go on to the kind of generalizations that we're looking at. For one thing, if you smooth all the crossings in the state by using the markers to give an instruction for smoothing the crossing, then you will get one single curve, one single connected curve, what I call a single cycle. So the states that I have described for you, which come naturally from Alexander's original determinant formulation, these states are single cycle states of the diagram. They're in one-to-one correspondence with that. Furthermore, and this is important for that black hole sign parity result, you can get from any state to any other state by marker exchange moves or clocking moves like this. You have a marker in this region and a marker in an adjacent region. You interchange them and you again have a state. And the clock theorem says that any two states are related by a series of clocking moves. There's a bit more to it than that, but then you can check after you've proved it that that shows you that the parity of the number of black holes is indeed correct for the determinant. There's a further structure that's important for these states, which is that if you think of single cycle smoothings, then you can go from any one to any other one by bigger jumps, which then can be factored into the smaller clocking moves. The larger jump idea is very simple. You have a single cycle state. You might re-smooth it somewhere, and then it will become 2 cycles. And then you might smooth it again somewhere, and it'll again become 1 cycle. So you do a break and make and go from one single cycle state to another. The clocking move is a local example of that, and the clock theorem is telling you that you can go from big jumps like that to smaller ones. And it's worth seeing how that works. I think I didn't mention that the states are in one-to-one correspondence with trees in the checkerboard graph, but you can see how that works in this slide. Here's the checkerboard graph of a knot diagram, and here is a tree, a maximal tree in that graph. And you see that I have produced a state by using the tree to put down markers as I open it up. I put a marker here, I put a marker here, I move away from the root, putting down markers, and then I find that having put a tree on this checkerboard graph, there is a unique tree on the dual checkerboard graph, the white graph, and you do the same thing, and those two trees together produce the state. But I'm illustrating something else here. Here is the make and break for a tree. You can take a tree and add an edge. And if you added an edge, then there will be a cycle. So you'll have to remove an edge, remove some other edge, and you're back to a tree. That's the same as smoothing and then resmoothing. And it gives you two states. The two states may be quite far apart, but you can get from one to another by a series of clocking moves, which I've indicated by these little arrows at the bottom of the slide. Well, all that combinatorics of states is actually very interesting and worth talking about for other reasons, but I just wanted to give you an introduction to that here. All of that kind of thing works for natoids, where you start with 1-1 tangles, and then the states become paths that start at one end and go in a single pathway, never crossing or crossing over to the other end. So now what we have is a permanent formula for the original invariant. I'm using W and B now. Notice the minus sign, and B is the inverse of W. Here it's the same calculation I was showing you a moment ago, but since I have the signs already in the state sum, and since the rook non-attacking rook patterns on the square matrix correspond to the states, we have that we can write down what amounts to the same kind of formula as Alexander as a matrix, but then you take the permanent of that matrix and you get the state sum. So for calculating various examples, this is quite useful to when you're working with the generalization, because you still can give it to a computer and you don't have to draw pictures of all the states or anything in order to get the invariant. In this case, this is illustrating that we are getting the Conway polynomial because, as you see, when I calculated it with these weights, we got a formula involving W minus W inverse, which is the Z for the Conway polynomial. So you can always say this in terms of a permanent. And now here's an example of some of the generalization. Here's a natoid. And in this natoid, I have worked out the polynomial, and we're doing it in exactly the same way, but let's watch what we did. We only eliminate one region rather than two because there's this one region at the endpoint. And the natural way to do it for a natoid is to have the special region be at the endpoint. And we'll talk about the natural question, what would happen if I put it at the other endpoint in a moment. But let's look at this. Here's the endpoint. And I am examining what the weights are going to be here for that. And at this endpoint, there are two weights. There's 1 and there's minus S inverse. So I want to explain to you what it looks like in terms of a state sum and what it looks like in terms of a permanent. For the permanent, for the algebra, you take the sum of the weights that are available in the region. So if the region, like this endpoint region, has more than one weight in it, you take their sum. So you get 1 minus S here. Here you get an S in A and you get a 1 in B. And you see the same thing happened over here at 2. You got a 1 plus S in B and so on. And we're not playing the game on A, and we take the permanent on here, and this gives us the state sum, and it gives us a polynomial. And that polynomial is now not as symmetric as the Alexander polynomial, which is to the good. It's a polynomial in the variable S or W. In this case, what you see is the verification that this natoid is not equivalent to its mirror image, because, as you see, the polynomial is not the same as what you would get if you substituted S for S inverse. I'll state the result in a moment, but it does detect chirality. If it's a larger one, use the same algorithm with the permanent. If it's a larger one, then you can hand it to the computer and ask for the permanent. You can also write out all the states. In some cases, I will. In fact, here's a small one, and we will. But the result is that if you have a mirror image natoid, switch all the crossings, then that will be the same as the original one with W inverse substituted. Change the variable to W inverse. So in this case, of the very simplest natoid, we're detecting its chirality in this way. Now we're going to generalize this even further, and I have to. You may give me a hint about how much time. I'm assuming I could go for another 10 minutes, probably.
Yeah, 20 minutes.
How much more?
20 minutes. You have 20
Oh,
minutes.
20 minutes. Okay, fine. So let's say that a diagram is admissible if the number of unstarred regions is equal to the number of crossings. That, of course, is what I want in order to have states. A diagram is admissible if it has states. So now the observation is that all that we did before works for admissible diagrams, but in the original case, when the stars are adjacent, you could have chosen any two adjacent regions and you were getting the well-definedness of the Alexander polynomial. In the case of the natoids, we had a very special choice for starred regions, namely the endpoints, and then we got an invariant of natoids. But in other cases, we can look at diagrams which are not allowed to move over the stars, and then we will have invariants of those, even though the stars are not in adjacent regions. And we'll see an example or two of those and different contexts in which you can do that. So I haven't said anything new in this slide. We'll continue. Here's the standard example. We already did it before, but now I'm doing it by adding up all the states. Before I wrote the permanent. Now that's the example of the Conway polynomial of the trefoil knot. And of course, you could do it with a permanent. But now here's a new example. Now I put the stars in two regions that are not adjacent to one another. And you can do the same thing, of course. You can write down, you can either enumerate the states, or you can write down the permanent and compute it. And in this case, you find that the permanent is W cubed minus W to the minus 3. And that tells you that it's chiral, because when you substitute W to W inverse, you get a different result. And this is a special diagram. This is admissible. The knot is allowed to move, but it's not allowed to move over the stars. So it's an object in a different space. You can interpret this as being in a handle body, if you like, where you've drilled holes in the thickened plane. But now we have a wide range of things that we can do with admissible diagrams. We can put them in various circumstances. Here's a generalization of what you just saw, and in fact, the state version of it. I have here 3 crossings and the stars in non-adjacent regions. And as you see, there are only 2 states. There's one where all the markers run forward and the one where all the markers run back. And that's where we got W cubed and W to the minus 3. And if you had n crossings and the stars in this place, you would get W to the n and W to the minus n. And this is a good example of something that satisfies the Skene relations. It does. And you can check that this formula for this invariant is a function of the Skene relations. That's a nice example. Here's another example. Here I have these spiral examples where I have stars in these little loops. All right. And so this has the feel of being something like a natoid, in that the diagram is free to move around everywhere, but it can't go over the stars. The stars are locked in these little loops. You can make many examples of this kind. In the case of this spiral, the matrix pattern is a diagonal of z's and ones on either side of the diagonal, where the z is w minus b. And you can then see how to compute the polynomials recursively using the Skene relation, which still is satisfied under these admissibility conditions. Nice example, and they're all chiral. Here's another method of obtaining admissibility. You see, now the question becomes, how do I get admissibility? If I can get admissibility, I have an invariant. So I'm back to a classical diagram, and I take a trident. My trident is a little handle addition to the plane in this form. And when I add that handle to the plane, I'm in a double torus. And these three regions where the base of the trident touches now become one region. And so now you can see that the number of faces is equal to the number of vertices. And consequently, you can write down your matrix. And there are no starred regions exactly. It's just that you have forced the number of faces to be equal to the number of vertices. And you can take the permanent and find that you got an invariant of this knot, which is now in a thickened surface of genus 2. That's just the same example. I must apologize perhaps for the rough form of some of these diagrams. They will get cleaned up as we finish writing the paper. What about invariance? Well, it turns out that invariance is just a matter of local verifications about the state sum in relation to where the markers are. And that's why you can prove that as long as the diagram is admissible, you have invariance under the Reidemeister moves. There's some combinatorics here. I'm just giving you a flavor on this slide of a bit of that combinatorics, including what happens under the 3 move, where you have to watch triplet cases like this and see that the vertex weights contribute equally on either side of the move. Here's a nice example for exploration. I have taken a natoid where I put the starred region on the left one. I put the starred region somewhere in the middle, and I put the starred region on the right. And I calculate the 3 polynomials. And as you see, I get w plus w squared minus w inverse for the left star polynomial. I get minus w inverse plus w to the minus 2 plus w for the right star polynomial. And the middle one is something different, of course. But it is, as I said, natural to ask, if you're going to define the invariant for a natoid, shouldn't you ask what will happen if you put the star at the other end of the natoid? Now, if you put the star at the other end of the natoid and the arrow was going out, and you decided that that was your well definition, then it ought to become equal, the same. And that's our conjecture, which we haven't yet proved, that in this form, the conjecture looks like this, that delta K3, nabla K3 at minus W inverse is nabla K at W. Minus W inverse, the substitution minus W inverse is exactly what happens when you reverse the orientation of the diagram. That's not hard to see. So that this is the same as saying that if you were to take the other end and write the arrow in the opposite direction so that it goes out from the other end, then you would get the same invariant, the same polynomial. That appears to be correct, and we're still puzzled by the absence of at least a proof by us. So the natoid, actually the natoid conjecture is like this, that I meant double prime, of course, here. I'm between this one and that one. And then it can actually be stated at the level of the W and the B without asking that W and B multiply to be equal to 1. But it amounts to saying that it's well-defined when it's an invariant if this is going out here and going in there. Oh, I see. Pardon me. I really meant what I wrote, because what I've written here is star on the left, and here is star on the right, but with the outgoing arrow, and here with the ingoing arrow. And it's delta K prime that it has the reversal in it. Anyway, it's an intriguing conjecture, and it appears to be true at a combinatorial level prior to the WB, which makes everything invariant. Now, there are other ways, as I said, the key here to this exploration is admissibility. I can create admissibility for a multi-noptoid. This is a multi-noptoid. These two guys are in different, have their ends in different endpoints, and these are two ends in different endpoints, and there's more than one arc, a multi-noptoid. And you see that now the number of faces is equal to the number of vertices. A little other characteristic calculation can show you, maybe I have a slide for it, exactly when you get admissibility. But one way you get admissibility is planar noptoids, multi-noptoids, 2 arcs, and then you get admissibility with no stars. And we have an invariant for that. There it is. And often seeing chirality for that. Yes, this is what happens in general. If you had the graph, the knot diagram, tightly embedded so that all of the regions were disk-like, then you will find that the number of faces minus the number of 4 valent vertices is 2 minus 2g minus k over 2, where k is the number of endpoints. And so from that, you can find all sorts of different cases of admissibility. Here's another thing that happens. I did a calculation here on a connected diagram because I needed a connected diagram in order to have admissibility. If I let this go by a Reidemeister 2 move, I have a disconnected diagram and I don't have admissibility and I have no definition. But on the other hand, you can argue that it doesn't matter where I slid it together if you think of it as being apart. I can slide it together and then get from one of them to another by Reidemeister moves. So I can define, and then they will give me the same result in their own little category of admissible diagrams. And as a result, we can calculate an invariant for this pair of noptoids that are in the plane. And we find this non-trivial result for this pair of noptoids that are sitting in the plane. You can check it one way or another. And then you can think about that. That's an interesting thing to think about. Here are these 2 noptoids and they're in the plane. And if it was only one of them, they'd be trivial because, I'm sorry, really in the 2-sphere. They are in the plane, they're very non-trivial, even only one of them, because there's no way to take that outer arc and slip it around. On the 2-sphere, a single one of those is trivial because it can be swung around the 2-sphere. But if you have 2 of them, they're obstructing each other's swing around and they're not trivial. And we just proved they're not trivial in this calculation a moment ago. That's actually working in the 2-sphere. But you can do it other ways if you want to. You can use the Jones polynomial, bracket expansion of the Jones polynomial, and also prove that it's non-trivial. When you do it that way, this is a digression, thinking of doing the Jones polynomial kind of state sum, then you get loops around arcs And if you can't remove the loop from the arc up to isotopy in the space in which you're working, then you have to think of arcs surrounded by nested loops. Another idea of Churaev's in the case of connected natoids, and this is a slight generalization of the same idea, where the category of loops around arcs can be non-trivial, even in the two-sphere, if there's more than one arc. We already made this remark about the Euler characteristic. Here's a nice example. A knot embedded in the torus. In the case of the torus, F equals V, as long as it's disk-like embedding. And so here's a nice knot embedded in the torus, in the thickened torus, and it has a non-trivial invariant, and it's seen to be chiral by our method. Now, the interesting connection here is that natoids and knots on a torus are related to one another. If you have a natoid, you can make a knot on a torus by adding a tube to the plane and running a line that connects the two ends of the natoid together along the tube, and then you have a knot in a torus. So knot diagrams on a torus, or knots in a thickened torus, can represent natoids, but knots in a thickened torus are also, there are many examples that are not representing natoids. So there's two kinds of phenomena going on here. You can take your natoid and make it into a knot on a torus. If you do, in the case of this natoid, then you find what we found before, that we're getting some invariance of the natoid in relation to the invariance of the knot in the torus. And the relationship is as follows, that that the guy that's in the torus is actually equal to the sum of the evaluation of the natoid with the star at this end, plus the evaluation of the natoid with the star at the other end, which we were considering before. And then that ends up being, by our conjecture, equal to the other evaluation of the natoid. But anyway, the main point is that when you evaluate in the torus a natoid, the evaluation of it is actually the sum of two natoid invariants, one from one end of the natoid and one from the other. Not hard to see by thinking about what we were really doing when we made these state sums. So the natoids and the knots in the torus are closely related, but there are knots in the torus that are not natoid, natoids. This is not the closure of a natoid, this knot in the torus. This is an interesting knot in the torus in that its Jones polynomial is equal to 1. It's the least complicated version of the Jones polynomial of it is equal to 1. And we can ask, well, what does our invariant do? And calculate in the same way I've described to you, write down the permanent or write down all the states and take the permanent. And we find that we get a chiral, non-trivial knot in the torus. That's what this Mach-Alexander polynomial tells us. Whereas the simplest Jones polynomial can't see it. So this is a good example of how this invariant gets around. That's the same one, redrawn a little bit. And maybe this is a good place to wind down. One can use higher genus, but in higher genus, you have to cut down the number of vertices in order to get F equals V. In order to get admissibility, you need to have fewer vertices that are in play. So that means that you can decide to knock out some nodes knock out some crossings in the diagram and make them into inactive nodes. And these are graphical nodes and they're very inactive. You're not allowed to move the diagram across them. You can use planar isotopy on them, but no knot theory, no sliding across them at all. And then you have invariance of such objects in higher genus surfaces. So these are the calculations for this guy on a double torus. And then you see something interesting. It's chiral in this form where I knocked out these two nodes. But if I knock out these diagonal nodes, the polynomial says, I don't know that it's chiral. And then, in fact, if you look at it, you realize, oh, it is achiral. It is equivalent to its mirror image by a 180-degree turn. So all the issues, the usual issues about chirality, can be explored here. As I said, you can think of a star as drilling a hole in a thickened plane and then getting handle bodies. And of course, this is something that people have off and on done with other invariants like the bracket polynomial. A problem that I'm interested in, but I think I'd best not try to give you a talk on it right now, is the following situation. We know that if you have a slice knot, a knot that bounds a disk in the four-ball, a classical knot, well then it's Alexander or it's Conway-Alexander polynomials of the form f of w inverse for using w. And this kind of Fox-Milner property seems to be true in these generalizations if you look for it. And I would like to be able to prove a theorem about that. But my problem is that I don't know a good proof, even in the classical case, of this theorem that uses only the state sum. So I'm back at an old problem that I would like to understand, to use the state sum alone to prove the Fox-Milner theorem. There may be a way to do this, but it ain't obvious to me. So let me just remind you of some small thing about that problem. Yes, the usual way in which we prove the Fox-Milner theorem geometrically is by thinking about ribbon knots where the singularities are very simple. It's a special class of slice knots that bound an immersed disk in three space, and then to modify there's a conjecture that all slice knots are ribbon. That's also open, still open. You modify the intersection of the ribbon with itself by putting a hole and making a higher genus surface whose boundary is the knot. And then you use that higher genus surface and its nice properties to show by using the Seifert pairing that the Alexander polynomial has that form. That's a usual kind of proof, but this is far away from the state sum. And I don't know how to conceptualize the state sum in relation to slice knots to get a proof of the theorem that is indeed true for it in the classical case. One can play games with skein theory and see a lot of evidence for Fox-Milner type phenomena. And it is at that point that I think it's better to not worry you about the skein theory. And just conclude. So it would appear that for knottoids and some of the generalizations, the evaluation is NP hard and really seriously involves that permanent. It's not a determinant anymore. That needs some analysis. The path state structure or the marker state structure that I've been using can be used to define at least for nautoids, a Floer homology with the states generating the chain complex. I think that that's to be expected. And we'll see what happens to that. It is the case that combinatorial differentials have been given at least on the tree structures for some invariants that are related to not Floer homology. And so that's a next stage in this investigation. So that's a good place to stop with these questions, and obviously a lot of other questions that are implicit here. As I said, just to conclude, we started with this old state sum, which is nice and works for classical knots, and we notice that it works for admissible diagrams where the number of vertices is equal to the number of faces. However you make those diagrams admissible, and that gives rise to a range of different topological situations in which you can define invariants, not the least of which is nautoids and multi-nautoids. I'll stop there.
Thank you. Thank you, Professor Kauffman, for an interesting talk. Any questions? So is it possible to define a determinant also using this Mock-Alexander polynomial? For this
let me hear the question again. Is it possible, to define
determinants for this?
Oh, you mean, I guess you mean something like this. Take the case of the nautoid. Is the nautoid, which we have defined as a certain permanent, is it actually a determinant? I don't think so. In other words, now, of course, I could be wrong, but in the state sum, in the states, I no longer have the parity result anymore. So I can't go back and say that I'm calculating a determinant. The signs that are working in my state sum are working for their own reasons, and they don't translate back into a determinant. That doesn't mean there might not be some other way of formulating a determinant that gets that invariant, of course. But I don't think so. That's what I was saying. I think that we're looking at the sort of canonical NP-hard problem that you left the world of determinants for the world of permanents, and you're not getting back.
Any other questions?
I have a question, if possible. So there are a lot of connections between Alexander polynomial and other properties of knots. For example, slice knots and the homology. And in particular, there is nice relation between Wirtinger representations and Fox derivatives and Alexander polynomial. It's one of the approach how to construct it. Do you expect some theory related to groups? So is it correct to say that some of your Alexander-like polynomial can correspond to some group presentations related to knots?
Well, the original one is related to the Dane presentation, and one can trace how that happened. But at a certain point, one said, "Oh, I'm taking this combinatorics," and then you could ask, well, having smoothed out the combinatorics the way we did and made it very nice as a state sum, is there another way to get back to the Dane presentation? I'm raising that question again for myself, actually, because it may be that that something like a Dane presentation group for the nautoids will be related to the invariants for the nautoids.
Okay, thank you. And another question, do you expect some nice Floer homology for nautoids?
I don't know about nice, but over the last years, people have found how to define combinatorial differentials on what amounts to the marker state complex, because the original definition of Ozlov and Szabo was on the complex whose generators were the marker states for a classical knot or link. You'll recall. And the differential, it wasn't obvious. It was up in the symplectic geometry. But then there have been a number of different forays into defining it combinatorially, all of which are a bit complicated. I've been trying to look at the ones that aren't as complicated, and then get to looking at the ones that are more complicated. The least complicated one that I've found is the one by Kriz and Kriz. And they don't claim to get Floor homology. They claim to get a homology that's related to the E3 term in one of those spectral sequences. But it is a link homology. And they get it by a differential on the trees in the checkerboard graph, in the classical case. And so I'm puzzling over this, as anybody would. And maybe the next time I talk, I could tell you something about it.
Thank you.
Okay, thank you. It's a wonderful talk.